Welcome to Lecture 12 on how to read and do proofs. Welcome back, everybody. You're about to learn a new proof technique which is related to the quantifier for all. So to motivate this technique, let's look at the following question. What is the sum of the first n positive integers? So here's what we're looking at. What is the sum of the first integer? What's the sum of the first two integers, the first three integers, and the first n integers, and so on? Now, the first integer, we can simply get that sum very easily. The second one, we can get the sum very easily. The third one, we can get the sum very easily. But what about down here? What is the sum of the first n integers? What we'd like to have here is a formula in terms of n. That takes a little work and creativity to find, but there actually is such a formula, and here it is. N times n plus 1 over 2. But the question for today is, how do you know that that formula is correct? In fact, how do you know that for every integer n greater than or equal to 1, 1 plus 2 plus 3 up to n is equal to n times n plus 1 over 2? Let's label these statements for reference purposes. If you think about proof techniques, in general, how can you show that for every integer n greater than or equal to 1, some statement p of n is true?
The choose method?
Correct. This would be the choose method because you need to show that for every object with a certain property, something happens. So you could do this with the choose method. However, what you're going to find today is that because the objects are integers greater than or equal to 1, we have a better proof technique. Another way you might show that all of these statements is true is by proving each one on the list. For example, what I would like to do is check if this formula right here works for each of these statements. In other words, when n equals 1, does this formula give me 1? When n equals 2, does that formula give me 3? When n equals 3, does that formula give me 6? Well, let's check that. So for n equals 1, let's put 1 into this formula. We get 1 times 1 plus 1 over 2, otherwise known as 1. So that formula works for n equals 1. Let's check this formula for n equals 2. Everywhere you see an n, put in 2. 2 times 3 over 2 is in fact 3. Formula works for n equals 2. Let's try the formula for n equals 3. 3 times 3 plus 1 over 2 is 3 times 4 is 12, divided by 2 is 6. Sure enough, you get 6. So I have just proved that p of 1 is true, p of 2 is true, p of 3 is true, and you have to keep going. However, do not do this for homework. You will be busy for a very long time. We can't do this. What can we do? Use mathematical induction. This is a new technique that's going to be very effective when you want to show that for every integer n greater than or equal to 1, some statement is true. So here's the idea of induction. Rather than proving that every statement on the list is true, which we don't have time to do, the idea of induction is to create a machine that has the capability of doing that. If I gave you such a machine and said to you, this machine is capable of proving every statement on the list, you wouldn't need for me to prove every statement on the list because you would know that the machine could do it. So the idea of mathematical induction is to construct this machine. Make sure that the machine has the capability of proving every statement on the list. And let me show you what that means. So to get the machine started, what you have to do is manually show that p of 1 is true. You actually have to go and prove that the statement is true for the very first value of n equals to 1. And once you know that p of 1 is true, what we plan to do is put that into the proof machine and let the machine prove automatically that p of 2 is true. And as soon as we know that p of 2 is true, what we plan to do is put p of 2 into the proof machine and let the proof machine show us that p of 3 is true. And we keep doing this until eventually the machine proves that p of n is true. We'll put that into the proof machine, and hopefully the proof machine will show us that p of n plus 1 is true, and the proof machine can keep on going. So that's the idea of mathematical induction. Notice that by the time the machine has to prove that P of n plus 1 is true, it will already have shown that P of n is true. And so here's what this means. When you do a proof by induction, it requires two steps. The first step is to manually show that P of 1 is true. And after you do that, the next step is to assume that P of n is true and show that P of n plus 1 is true. Then the proof machine will have the capability of showing every statement on the list. It already knows that P of 1 is true, and because P of 1 is true, P of true is true. And because P of 2 is true, P of 3 is true, and so on. So if you can do these two steps, you will have constructed the proof machine. And what we're going to do now is look at the details of how to do these two steps. So let's talk about step 1 here. How do you go about proving that P of 1 is true? Well, this is actually very straightforward. Look at the statement you're trying to prove, and everywhere you see the integer n, replace it with the number 1 and see if the resulting statement is true. Let's take an example. You want to prove that the sum of the first n integers is n times n plus 1 over 2. So what we need to do to verify that P of 1 is true is everywhere you see an n, put in the number 1. And that becomes the statement P of 1. And now you have to check if that's true. What is the left-hand side? The sum of the integer 1. What is that?
1.
1 on the left. And what is this on the right?
1 as well.
1 as well. And there you have manually shown that P of 1 is true. And this is usually so easy that an author, when they write this up, will say, the statement is clearly true for n equals 1. They won't even write the details because it's, quote, obvious. This is very typical. Let's turn to step 2. This is the more challenging step. In this step, you should assume that P of n is true, and you have to prove that P of n plus 1 is true. So write that down. Assume that, in this case, the sum of the first n integers is, in fact, n times n plus 1 over 2. That you can assume is true. You have to show that P of n plus 1 is true. So how do you write down P of n plus 1? Everywhere you see an n, you should replace it with n plus 1. So I have to show that the sum of the first n plus 1 integers is equal to n plus 1 times n plus 1 plus 1 over 2. And let's just clean this n plus 1 up by making it n plus 2. So I have to show that the left-hand side here is equal to the right-hand side here. All right, so what I propose to do now to show that P of n plus 1 is true is I propose to start with the left-hand side of P of n plus 1 and eventually make it equal to the right-hand side. There's a special way in which you should do that. The idea is to use the fact that P of n is true. And how do I use the fact that P of n is true? I want to rewrite the left-hand side here in P of n plus 1 in terms of the left-hand side here in P of n. So how is the left-hand side here related to the left-hand side here? How is the sum of the first n plus 1 integers related to the sum of the first n integers?
The sum of the first n plus 1 integers includes the sum of the first n integers plus n plus 1.
Exactly. The sum of the first n plus 1 integers is equal to the sum of the first n integers plus n plus 1. That's called relating the statement for n plus 1 back to the statement for n. And this is the key to mathematical induction. Now you can use the fact that the sum of the first n integers is equal to n times n plus 1 over 2 by replacing this sum with n times n plus 1 over 2. And that's called using the induction hypothesis. P of n is the induction hypothesis, and you're assuming this is true. And here is where I have used it. I replaced this sum with n times n plus 1 over 2. The rest of this proof is algebra to go from here to here. In fact, if you just factor out the n plus 1, you get this. And if you write this over a common denominator, you get this. Let me summarize the two steps of a proof by mathematical induction. First, show that the statement is true for n equals 1. That usually is pretty easy to do. Most authors will simply say the statement is obviously true for n equals 1. Then assume that the statement is true for n. Show that the statement has to be true for n plus 1. And how do you do that? Start with the statement for n plus 1 and relate it back to the statement for n. Then use the induction hypothesis that P of n is true, and that should help you show that P of n plus 1 is true. Again, the time to use mathematical induction is when you want to show that for every integer n greater than or equal to 1, some statement P of n is true. Then you should think about using mathematical induction. All right, let me show you some variations on mathematical induction. It's not necessary for the statement to start at 1. You might want to show that P of n is true for every integer n bigger than or equal to some initial integer n0. If that's what you want to show, the only difference is that when you do step 1, you simply prove that P of n0 is true. P of the very first possible integer is true. Then, when you do step 2, you can use the fact that n is bigger than or equal to n0 if necessary. Let's do an example. Is the following statement true? For all integers n bigger than or equal to 1, 2 to the n is bigger than n squared. Let's check this. Is this statement true when n equals 1? Is 2 strictly bigger than 1? Yes. How about n equals 2? Is this statement true for n equals 2?
No.
How about n equals 3?
No.
So this statement is clearly not true. However, it is true that for all integers n bigger than or equal to 5, 2 to the n is bigger than n squared. That is a true statement. And now let's prove it by induction. So how does induction work? 2 steps. First step, show that the statement is true for the very first value of n, namely 5. The statement is true for n equals 5 because 2 to the 5th is 32, which is bigger than 25, which is 5 squared. That's the first step of induction. The second step of induction is to assume that the statement is true for n. So I should assume what?
2 to the n is greater than n squared.
That's correct. And you have to show that P of n plus 1 is true. What is P of n plus 1 here?
2 to the n plus 1 is greater than n plus 1 squared.
2 to the n plus 1 is greater than n plus 1 squared. And let's just write this out. N plus 1 squared, of course, is n squared plus 2n plus 1. Okay. Now, what I propose to do, just like we did in the previous proof by induction, is start with the left-hand side here and show that it is greater than the right-hand side. So let's start with the left-hand side. And in order to show that it's greater than the right-hand side, what you want to do is relate this 2 to the n plus 1 back to 2 to the n. Can somebody tell me how is 2 to the n plus 1 related to 2 to the n?
2 to the n plus 1 is equal to 2 times 2 to the n.
There is the relationship of 2 to the n plus 1 to 2 to the n. And now you can use the induction hypothesis that 2 to the n is greater than n squared. So this becomes greater than 2 times n squared. 2 to the n is bigger than n squared, so 2 times 2 to the n is bigger than 2n squared. The rest of this proof involves showing that 2n squared is bigger than n squared plus 2n plus 1. And that also involves a bit of work. Is that really true? Is it true that 2n squared is greater than n squared plus 2n plus 1? The answer is yes, because you can actually prove that for all integers n bigger than or equal to 3, n squared is bigger than 2n plus 1. And so when you add another n squared here to both sides, 2n squared is bigger than n squared plus 2n plus 1. So you need to show this lemma by induction. And I'll leave that as an exercise for you to go home and do. Another variation of induction arises in a notational setting. Some authors like to assume that the statement is true for n minus 1 and show that the statement is true for n, as opposed to assuming the statement is true for n and showing it's true for n plus 1. Both are equally good. What's important is that if the statement is true for one value of the variable, it's automatically true for the next variable. Now, in some problems, it's actually difficult to relate p of n plus 1 back to p of n. This can be somewhat challenging. But sometimes it's possible to relate p of n plus 1 not to p of n, but to one of these earlier statements. Let's say p of j. In that case, when you can relate p of n plus 1 back to some earlier statement, let's say p of j, you can in fact use the assumption that p of j is true, because by the time the machine has to prove that p of n plus 1 is true, look at what it will already have proved. P of 1 is true, P of 2 is true, P of 3 is true, P of 4 is true, P of n is true. You'll know that all of these statements from P of 1 up to P of n are all true. With strong induction, when you want to show that P of n plus 1 is true, you can assume that all of the statements from P of 1 up to P of n are true, because the machine will already have proved all of them. And that can be helpful if you want to relate P of n plus 1 not to P of n, but to one of these earlier statements. Let's take an example of doing that in the context of reading a proof. Here's the definition of a prime integer. An integer p greater than or equal to 2 is prime if and only if the only positive integers that divide p are 1 and p. And here's what we want to prove. Any integer n greater than or equal to 2 can be expressed as a finite product of primes. So again, you should recognize the key words in the backward process. So you have to show that for every integer n bigger than or equal to 2, n can be expressed as a finite product of primes. Here is a written proof that I'd like you to take a few minutes to read and see if you can figure out what the author is doing. Okay, our goal is to understand these statements in the context of proof techniques, and in this case, obviously, in terms of induction. So, to begin with, we need to be sure we understand what the statement P of n here is. Can somebody tell me what is P of n from the proposition?
N can be expressed as a finite product of primes.
N can be expressed as a finite product of primes. Let's interpret the statement S1. The statement is clearly true for n equals 2. What is the author doing here?
Showing that the statement is true for n equals 2.
Yes, the very first value of n is 2, so the author is claiming that 2 can be expressed as a finite product of primes. Can it? Yes, it's just 2 by itself. So this statement is clearly true. Now let's go to statement S2. The author says, assume that every integer k equals 2 up to n can be expressed as a finite product of primes. What is the author doing here?
He's assuming that by strong induction that for all the values of k greater than 2 are true.
Yes, this is strong induction. The author is assuming that the statement, what statement? P of n. The author is assuming that the statement P of n is true not just for n, but for all the values up to and including n. This is strong induction. The author is assuming that P of 2 is true, P of 3 is true, P of n is true. What does the author have to do next?
Show it's true for P of n plus 1.
Show that P of n plus 1 is true. And what is P of n plus 1?
N plus 1 can be expressed as a finite product of primes.
Exactly. N plus 1 can be expressed as a finite product of primes. Now let's read S3 and see what the author says. If the integer n plus 1 is prime, then the result follows. Is that true? If n plus 1 is prime, can n plus 1 be expressed as a finite product of primes?
Yes.
Yes, it's just itself, right? There's nothing else to prove. If n plus 1 is prime, then the result follows. So now what do we have to look at?
When n plus 1 is not prime?
What happens if n plus 1 is not prime? Is it true that when n plus 1 is not prime, can n plus 1 still be expressed as a finite product of primes? Let's find out what the author says. The author says if n plus 1 is not prime, then there are integers p and q between 2 and n for which n plus 1 can be written as p times q. Where does this come from?
The definition of being not prime?
What it means for the integer n plus 1 not to be prime. Exactly. Now the author writes, but then there are primes, say P1 to PR and Q1 to QS, such that P can be written as this and Q can be written as this. Any idea where this comes from?
It came from the induction hypothesis?
It came from the induction hypothesis because P is an integer between 2 and n, and so P, by the induction hypothesis, can be expressed as a product of primes. Q is an integer between 2 and n, and by the induction hypothesis, Q can be expressed as a product of primes. This is precisely using the induction hypothesis. And finally, the author says, it now follows that n plus 1 equals P times Q, which is equal to all of this. In fact, that's nothing more than working forward from here, n plus 1 equals P times Q, and then substituting this for P and this for Q to write this. And what is your conclusion when you look at this? It now follows that n plus 1 can be written as what?
A product of primes?
A product of primes. And that is exactly what the author had to show for the second step of induction. And that completes the proof. So let me summarize a proof by mathematical induction. First of all, when should you use a proof by mathematical induction? Whenever you want to show that for every integer n bigger than or equal to some initial integer n0, some statement P of n is true. That's the time to think about using induction. And how do you actually use induction? 2 steps. First, show that the statement is true for the very first possible value of the integer, in this case, n0. Actually show that the statement P of n0 is true. Then, for step 2, you should assume that P of n is true and prove that P of n plus 1 is true. And the key to doing that rests in your ability to relate the statement for n plus 1 back to the statement for n. When you try to show that if P of n is true, then P of n plus 1 is true, you can also use the fact that n is bigger than or equal to the initial value n0 if you need that. And you can also use strong induction, whereby you can assume that not only is P of n true, but all of the statements before P of n are true. P of n0, P of n0 plus 1, all the way up to P of n. Any questions on mathematical induction?
Can you use induction for something that doesn't have a lower bound? It could be true for negative infinity or up to.
That's a good question. The question is, can you use induction to show that, for example, P of n is true for every integer n equal to 3, 2, 1, 0, all the way to minus infinity? The answer is yes, and here's how that would work. You would first show that the statement is true for the very first starting integer value, in this case 3, show that P of 3 is true. But now what you would have to do is assume that P of n is true and show that P of n minus 1 is true. So there are these kinds of modifications and variations on induction. Great question, Luke. Yep. In fact, if you want to have some fun, here's some variations to think about. How would you use induction to show that a statement is true for every even integer or for every odd integer greater than or equal to some starting point, right? And in fact, how would you use induction to show that a statement is true for every integer? Interesting. Think about these. These are very good things to play with. That completes this lecture.